Hi, we are answering other questions about Lewis structures, including what's its three-dimensional shape, what primary intermolecular force acts on each, and then ranking them from slowest to fastest evaporators. So let's start by figuring out how many Lewis, or what the Lewis structure looks like for each one. We'll start with bromine, Br2. So bromine has 7 valence electrons. That's 7 times 2 because there's 2 of them. So that equals 14 dots. Really, there's only one way to arrange something with 2 things, which is just tack them together like that, and then add the dots and hope that it equals the right number. So always give everything 8 to start with, and then hope that it equals this number right here. And in this case, it does 2, 4, 6, 8, 10, 12, 14. So it's got 14 dots, and each bromine has 8. So we know it's a valid Lewis structure. So there's our Lewis structure for bromine. Next one is pH3. So phosphorus is 5, and then hydrogen is 1, but there are 3 of them, so that equals 5 plus 3, which is 8. And you put your phosphorus in the middle, and since it says H3 here, then we're going to add 3 H's there. So each one is going to go on one part of the phosphorus. And then again, always give everyone 8 to start with, except hydrogen only ever gets 2. And then hope that it equals the right number. So right now, this phosphorus has 8. Each hydrogen has 2, which is what we want. And I used 2, 4, 6, 8 electrons to make it happen. So there's our Lewis structure for pH3. And then the last one for Lewis structures is SeS3, selenium, and then 3 sulfurs. So selenium is 6, and so is sulfur. So that's 6 times 3, or this whole thing would be 6 times 4, which is 24 dots. So I'm going to do it right here. Put selenium in the middle. There are 3 Ses, so add them. Or sorry, 3 sulfurs, so add them like that. Give everyone 8 and hope that it equals the right number, which is 24. So if you go through and count it after you give everyone 8, you'll notice that it gets 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. That's too many dots. So when you have too many dots, you need to make a double bond somewhere. We're going to make one right on the left side here. So you erase a set from each, and then you make the bond from where you just erase them. And so then that is the Lewis structure for SeS3. If you want to find the shape of each of them, the shape is just going to be based on the shapes chart, which maybe I could find real quick. Shapes chart looks like this, okay? And the shapes chart for here, we're going to look at each one individually. So this one is linear because there's only ever 2. If there's only 2 things, then you can only be linear. There's nothing to look up on the chart. It's just like connecting 2 points on a graph. Like there's only one way you can do it, and that is you make a line. And so when you connect 2 elements, you make something that's linear. On the next one, pH3, you count again how many things are bonded to the central atom only. So it's 1, 2, 3, 4 things bonded, and one of them is an unshared pair. So you check out the shapes chart, and we saw that there were, that's the wrong one. That's so embarrassing. It's this one. On the shapes chart here, let's see if I can clear this out. A thing I should have done before I started making this video. It's going to go up on YouTube. There we go. And on the shapes chart, we had 3 things attached and 1 unshared pair. So you go to, 4 things total and 1 unshared pair. So 4 things total, 1 unshared pair. And so that's going to be trigonal pyramidal for our shape. So if we go back to it here, we'd say trigonal pyramidal. Oof, that's brutal. Okay, and then the last one has 3 things attached and no unshared pairs. 1, 2, 3 things attached to the central atom, no unshared pairs. So according to our shapes chart, when you have 3 things attached and there's no unshared pairs, you are trigonal planar. Okay, so all this elements on the same plane. So trigonal planar is the name of this last one. Whoops. Okay. If you want to know about intermolecular forces on each, the intermolecular forces rules are pretty straightforward. Either it's symmetrical, and if it's symmetrical, it's going to be LDF, or it's not symmetrical, which is dipole-dipole, or it has a hydrogen bonded to an N, O, or F, and that's hydrogen bonding. So the first one obviously is symmetrical, cut it in half. Clearly there's bromines on both sides. So the first one is LDF only. And the second one is not symmetrical. If you cut it this way, then there's a hydrogen here and there's nothing over there. So that would be, oh well, it also has a hydrogen, but it's not bonded to an N, O, or F, it's bonded to a phosphorus instead. So it is just going to be dipole, dipole for that one. And then finally, you have something that's also not symmetrical. And it is, there's no hydrogens there, so it's going to be dipole, dipole. Okay, and then the last question is, how do you rank them from slowest to fastest evaporator? Well, if you're going to rank from slowest to fastest evaporator, that means that you're ranking them from strongest to weakest. Slowest evaporators are strong, and fast evaporators are weak for their intermolecular forces. So that being said, the strongest of these three, well, LDF, these strengths go like this. Hydrogen bonding is the strongest, then dipole, dipole, then LDF. So we're going to save this one for last because it's the weakest. But when you have two things that are in the same category, like these two dipole, dipole ones, you're going to go with molar mass as your second thing. So the molar mass, I don't know the totals, and I'm without my calculator, but you can estimate. It's not a problem. So phosphorus is 31. And there are 3 hydrogens there, so call it about 34. And this one has, for each sulfur is 32, and there are 3 of them, so that's already way more than 34. So if we're going from strong to weak, then this is going to be our strongest one. This is going to be our number 1 strongest intermolecular forces, or what do we say? We said slowest evaporator, and then number 2 would be the next highest molar mass, so that's this one. And then 3 would be, there's no more in dipole, dipole, so the third one is LDF. So there's your ranking from slowest to fastest evaporator. So kind of a rundown of lots of things that we've done so far for the intermolecular forces unit. We've got Lewis structures, we've got shapes, we've got intermolecular forces, and we've got ranking. This has been so fun. We'll see you soon. Okay, bye.